Hi, I'm Zi-Ting Chou, and in this video, I will be presenting GSNReRF, Generalizable Semantic Neural Radiance Fields with Enhanced 3D Scene Understanding. Let's review NeRF quickly. NeRF is a simple and effective 3D representation, which takes hundreds of images of a scene for training and be able to do novel view synthesis. The core concept is that tracing rays through each input image, sampling points along this rays, and feeding these sample coordinates into a neural network. This network predicts both color and density for each sample point, and with differentiable volume rendering performed along the ray, we can render a pixel color. This process is repeated billions of times while minimizing an L2 loss against the ground truth pixel color. Ultimately, the network encodes the shape and color of the scene. However, if we want to render a novel view of a different scene, the original NeRF falls short. This is where the generalizable NeRF comes in. The concept is that after training on multiple scenes, the model can directly render a novel view of an unseen scene using multi-view image of the new scene as input. PixelNeRF in 2021 introducing a method that leverages multi-view images of a various scene to train a model capable of generalizing to new unseen scene. The core innovation of PixelNeRF is that it infers a novel view of an unseen scene by conditioning the NeRF on pixel-aligned image features. Instead of starting from scratch for each new scene, PixelNeRF utilizing CNN to extract features from input images. These features are then used to inform the radiance field that which scene you are representing, allowing the generalizability. Our approach integrates the generalizable NeRF with semantic segmentation capability. Similar to generalizable NeRF, after training on multiple scenes, our method can directly render novel view image and semantic segmentation map of an unseen scene, given multi-view image of the scene as input. Our method consists of two steps. The first step is semantic georeasoning, which extracts pixel-aligned feature and valuable geometry cues for rendering. The second step is depth-guided visual rendering, where we design two sampling strategies based on the geometry cues to perform image and semantic rendering simultaneously. In semantic georeasoning step, we perform multi-view depth estimation. Similar to many existing depth estimation methods, image I1 to IK are fed into a shared CNN encoder to extract feature. These features are then fed into a cost volume aggregator to combine multi-view information and create 3D feature volume FV, which ultimately predicts depth maps of each frame, D1 to DK. This multi-view depth estimation can be supervised directly using ground truth depth maps or in a self-supervised manner, following the approach used in RC and VSNet. The depth map for each input image are then used to estimate depth map for the target or novel view, DT, by projecting each depth prediction back into 3D space and reprojecting them onto the target image plane. We obtain valuable geometry cue for rendering. Here we illustrate how we utilize geometry cue to enhance both image and semantic rendering. Traditional NeRF methods samples points along an array either uniformly or hierarchically. However, with our novel view depth estimation, we know where the array intersects an object. This allows us to avoid excessive sampling in an empty space. Instead, we sample points for image rendering x1 to xn based on a Gaussian distribution centered around the depth prediction value. Moreover, we observe a key difference between image rendering and semantic rendering. In image rendering, we must account for transparent or semi-transparent objects, requiring prediction for not just the first object's color, but also for other points nearby. Conversely, in semantic rendering, we only need to consider the first object that the array intersects due to the absolute occlusion nature of this text. Therefore, for semantic rendering, we sample only a single point xz to perform the rendering. Here are some results comparing our method with previous SOTA approaches. S-Ray in 2023 is the only other method similar setting as us, making it our primary comparison benchmark. The quantitative comparison table is divided into two sections. In the top half, it's important to note that S-Ray's official repository uses ground truth depth of each image as input, requiring ground truth depth for both training and testing. In contrast, our method uses ground truth depth only for supervision during training, with no need for ground truth depth during testing. In the bottom half, we remove the ground truth depth input from S-Ray, and our method adopts self-supervised depth loss for semantic georeasoning regulation. Our method consistently outperforms previous approach across all metrics on both real-world and synthetic dataset. Here are some qualitative results. These were obtained in a generalized setting, meaning the scenes were unseen during training. Thanks to our specialized sampling strategy, our image rendering quality significantly surpassed that of X-ray. Additionally, our semantic rendering results exhibit fewer artifacts and less fragmented. We also show fine-tuned setting results here. Due to our designed sampling strategy, the number of sampling points for image rendering can be adjusted after training without compromising the quality of semantic rendering. As shown on the right, when the number of sampling points is reduced, the image rendering quality of methods like GSNReRF degrades significantly, whereas our method maintains the quality. Additionally, as seen in the table on the left, when the sampling number is decreased to 4, our method achieves a 4-time rendering speed compared to X-ray, while still having superior image and semantic rendering quality. In conclusion, we present a novel framework named GSNReRF, which enables the simultaneous rendering of novel view image and semantic segmentation. Leveraging depth-guided visual rendering with two sampling strategies, our approach outperforms existing methods on both real-world and synthetic datasets. Thanks for your attention.